So, dear students, let us begin with the class again. And please do inform me in case if my voice is having a little bit discontinuity and the clarity may go. So, dear students, let us begin with it. Now, the topic which we will be beginning with is electromagnetic induction. As this particular topic was already taught, and once again, we'll be moving with it. Dear students, the first very basic fundamental we'll discuss is regarding what are the contents we will have to discuss in this chapter. Primarily, we will discuss about the magnetic flux, which is actually the main topic of the chapter. Then we will talk about the Faraday's experiment and the Faraday's law of EMI. Then Lenz's law, and then talk about Lenz's law and the law of conservation of energy. Expression for the induced EMF based on both the laws, that is Faraday's law and the Lenz's law. Then we will discuss about the method of production of induced EMF and the three important areas, that is how the magnetic induction how this induced EMF can be produced, and there will be three ways by which we will be producing this induced EMF. First, by changing the magnetic field. Second, by changing the area of the coil. Third, by changing the relative orientation of the coil with the magnetic field. This next topic will be eddy currents. That will be a theoretical topic. Then comes self-induction and the self-inductance. Similarly, we'll discuss about mutual induction and mutual inductance. Along with it, we will go with some additional information. This is brought to you by me, and I'm Saurabh Rai. I hope all of you will be able to see the slides. In case if the slide is visible to all of you, please do inform me. Please, any one of you can inform me whether the slides are visible. Is the slide visible?
Yes, sir.
Now let us talk about the first very basic topic, that is the magnetic flux. Now what is the magnetic flux is? Let us discuss about it. Magnetic flux is what? It is the number of magnetic field lines passing through the surface area normally. They are what? They are the number of magnetic field lines which are passing through the surface area normally. It can also be defined as the product of the area of the surface and the component of the magnetic field normal to that surface. For example, this is some conductor whose surface area is ds. This is the normal to the surface. And this is a magnetic field line making an angle theta with the normal of the surface. So with the normal, it makes component b cos theta with the normal. Now, you already know for the flux phi, the total flux phi will be equal to b into surface area. That will be d phi is equal to, for a small surface area, d phi. For the small surface area ds, the flux will be small, that is why it is written to be as d phi, and d phi is equal to b vector dot ds vector. Now why I'm writing here ds and b to be as a vectorial notation is because you already know that the field is a vector quantity, which we all know, and the second important thing is surface area, that is to a vector quantity because it is directed along the direction of the normal. So here we'll be writing vector dot vector. And you already know vector dot vector is a scalar quantity. So one thing needs to be very clear, that the magnetic flux is a scalar quantity, dear students. Furthermore, the direction of ds is along the normal to the surface, and n cap is unit normal vector. Furthermore, d phi, that is equal to b dot ds cos theta. Previous expression was giving you the vectorial form of the flux, but the second expression will give you the magnitude form of the flux. Furthermore, if surface area is not variable, it is a fixed surface area, it can be represented by a area along the normal direction. Then you can write here phi is equal to b vector dot a vector. Previously we have written d phi, that is equal to b vector dot ds vector. But once when the area is fixed, there is no variability, then you can write here phi is equal to b vector dot a vector. And furthermore, you can write here a vector to be as magnitude a in the normal direction. That means b vector dot a n cap. This you can write here for the value of the flux phi. Furthermore, when you will be removing the dot, you can write here ba cos theta. Positive flux, zero flux, and negative flux. Let me tell you, we can talk about the flux in three ways. If the direction of the field and the direction of the normal of the area are in the same direction, you can take it to be a positive flux. If the two, that is the field, magnetic field and the normal of the area is opposite to each other, then you can talk about, then you can say it is a negative flux. And once when the theta is equal to 0 degree, when the theta is equal to 90 degree, I should say theta is equal to 90 degree as well as theta is equal to 270 degree. And when you'll be placing cos 90 or cos 270, you will get the value 0. So phi is equal to 0 in this case. So dear student, there are three cases. First is the positive flux, second one is the negative flux, third one you can talk about is the zero flux. For zero flux, condition is very clear. That is, theta needs to be 90 degree or 270 degree. For positive flux, theta should lie in between 0 to 90 and 270 to 360 degree. Means it should be greater than 270 and less than equal to 360. In the prior case, it should be greater than 0 degree and should be less than 90 degree. In the negative flux, it should be lying in between, it should be greater than 90 degree and should be less than 270 degree. So this is the case for the negative flux. In shorter term, you can say like, if the field and the normal of the area are in the same direction, you can say it to be a positive flux. And if they'll be opposite to each other, you can say it to be a negative flux. And when the theta is 90 or 270 degree, it encounters the zero flux. Furthermore, dear students, if theta is equal to 0 degree and theta is equal to 0 degree, that is phi is equal to b dot a cos theta, that is phi is equal to ba cos 0 degree gives you ba. That is the maximum value of the flux. Furthermore, phi is equal to ba cos theta. Magnetic flux across the coil can be changed by changing number one, B, that is the magnetic field. Number two is area, and number three is orientation. So either of the three, if you change, the value of phi will change. Along with it, if you will be changing the combination, it means that B and A will be changed, A and theta will be changed, or B and theta can be changed. If the combination can be changed, or all the three can be changed, then the value of the phi will be changed. It means phi is dependent, and it depends on all the three quantities. Furthermore, my dear students, magnetic flux is a scalar quantity, as I have already told you. The SI unit of the magnetic flux is Weber, or you can say it to be Tesla meter square. CGS unit of the magnetic flux is Maxwell. Most importantly, 1 Maxwell is equal to 10 to the power minus 8 Weber. Magnetic flux per unit area, it means phi upon A, flux per unit area, is called magnetic flux density. And it is also termed to be as the strength of the magnetic field or magnetic induction. So one thing needs to be clear, that is phi upon A, that is flux per unit area is called the flux density, right? Most times when we talk about density, we divide the term by volume, but in this case, we'll be dividing it by area, right? Because surface is always having the area. It do not contain the volume. Now, let us talk about the next thing. Faraday's experiment, we need to understand. We already have discussed in the previous classes, but once again, let us go over it. You'll have to just focus to the polarity developing. In the first case, when the north of the magnet was coming closer to the coil, the north will be getting developed, right? Furthermore, when south is coming closer to the coil, south will get developed, right? Furthermore, let us move on to the next. Let us move on to the next. Here, what is happening? Just check it out. Just see the galvanometer. If you see the galvanometer towards the left hand side coil, the coil towards the left hand side, the deflection will be towards the right. And in this case, just check it out once again. Check it out once again. Coil is coming towards the north, deflection was towards the right. Which type of current is forming here? Anti-clockwise. If you see the direction of the arrows, it represents the anti-clockwise. Let us talk about the next thing. See the coil in the right hand side. Coil in the right hand side. If you see, when the magnet was moving towards the left hand side, the polarity developed in the closer phase is north. The polarity developed in the closer phase was north, if you see this side. Right. Now let us talk about the next thing. When this is going, now here what you'll have to do is just check it out. What you'll be doing is just check this particular area, right? You'll have to see this particular area, this galvanometer wala area, right? This is what you'll have to check. Now I'll be proceeding. Just check the galvanometer. The deflection. The deflection. The deflection. If you see the galvanometric deflection. The galvanometric deflection is toward the left hand side. and the arrow represents the clockwise direction. Clockwise direction of this coil and anti-clockwise direction in this coil, right? If you see. So this is what we need to understand. This is what we need to understand. This side as well as this side, right? Now let us talk about the next thing. Let us talk about the next thing. Furthermore, this is the case. What is happening here in this particular cases? Now, what I'm going to do, if you see this particular magnet, this is a magnet. Furthermore, you will have to keep your eye onto this, right? This means this magnet. Here you will have to see the north polarity will get developed, and here you will find the south polarity will get developed. Along with it, you will have to see the galvanometer. It means which sided deflection it will be producing. Just check it out. Magnet is coming toward the coil, north was getting developed. Just check it out again. Let me take you to it. Just check it out again. North was coming closer to the coil, north was getting developed. Right? Once again. See the deflection, the galvanometer. This you'll have to keep in your eye. See the deflection is towards the right hand side. So dear students, when the north was getting developed, when it is coming closer to it, here you were getting north pole, here you were getting south pole, then the deflection was towards right hand side, towards the right hand side. So now what are the basic observations? First thing what you'll have to keep in your mind, let us go with it. Magnetic flux linked with the coil changes. It means what is happening when the magnet was coming closer to the coil. When the magnet was coming closer to the coil, what do you observe? You simply observe that there is the development of the induced EMF. There was the flow of the current. Furthermore, let us talk about the observations. First observation, the relative motion between the coil and the magnet. There was a relative motion between the coil and the magnet. Next point, the induced polarities of the magnetism. It means you just have checked that what are the polarities getting developed. When the north was coming closer to the coil, the north was getting developed. Next, the direction of the current through the galvanometer and hence the deflection of the galvanometer. This was the third thing to observe. Fourth thing to observe was that the induced current or the EMF is available only as long as there is a relative motion between the coil and the magnet. If you simply see, let us go back. What is happening? This was the case. It is coming closer. Current was getting developed. Once again, let us move on here. If you see the direction, the deflection in the galvanometer means what you will be doing. You will be observing few things. First thing is the motion of the magnet and the coil. It means either the motion of the magnet or the motion of the coil, or the motion of both of them, right? And with the motion of both of them, what you will be observing, there is a development of the polarity. Just check north pole is getting developed. Along with it, there is a development of the current. Now, just check the galvanometer in the next case. Galvanometer is getting deflected. So these are a few things which one should always remember while studying all these points. So these are what the point to be observed. Now, the noteworthy point. Coil can be moved by fixing the magnet. It means what we'll be doing is, in the previous case, what you have done, you simply have moved the magnet. But in this case, what we will be doing? We are simply moving we'll be simply moving the magnet, right? So what is happening over here? In this particular case, what we just observed, we simply observed that the magnet was moving and the coil was stationary. But what you can do, note means the point number one, that is what you can fix the magnet and can move the coil. This can also be done. Both the coil and the magnet can be moved. This can also be done. But here, one point what you'll have to keep in your mind, that is, there must be the relative velocity between them. It means what you need to do is they should not be moving with the same velocity in the same direction. Right? They should not be moving with the same velocity in the same direction. Now, if they'll be moving with the same velocity in the same direction, for example, you are sitting in a bus, your friend is also sitting in the bus, both of you are moving with the same velocity in the same direction. Is there any relative motion between you two? No. He is also sitting there, you are also sitting there. There is no motion, means there is no relative motion. Though you both of you are moving, but actually there is no relative motion between both of you. Both of you are moving, right? But there is no relative motion. So what is most important for the production of flux? That is what there should be a relative motion. Now let us talk about the next thing. The third point is the magnetic flux linked with the coil changes relative to the position of the coil and the magnet. It means what you'll have to do is the magnetic flux linked with the coil changes relative to the position of the coil and the magnet. If the position of the coil and magnet will change, depending upon them only, there will be the change in the magnetic flux. If the change is more, flux will be more. If the change is less, flux will be less. So what needs to be more? That is what the relative motion between the coil and the magnet. Let us talk about the next point. The fourth point here is the current and hence the deflection is large if the relative velocity between the coil and the magnet and hence the rate of change of the flux across the coil is more. It simply indicates that if the motion is more, motion means what? Relative motion between the coil and the magnet. If it is more, flux will be more. Right? Let us talk about the next. The next here is what the Faraday's second experiment. What Faraday's second experiment says. If you see, this is the case. Now, if you need to focus to the key here, key means that K which is capped, means capped which K which is written over there. Just focus to this key. What is happening here? This is primary coil, this one is secondary coil, right? Now I'll be switching on the key. You'll have to focus here to the key, and the second focus of yours should be on the galvanometer. Just see it. When the key is connected, there is a deflection, right? There is a deflection, and the deflection was toward the right hand side in the galvanometer, right? Furthermore, this is the second case, right? When the key was taken out, the deflection was toward the right hand side. It means, now let me tell you what is happening here. Just check it out. This is the case, deflection was toward the right hand side, key was on. Second case, I'm taking out this, see the key is connected over here. Now what I'm going to do, key is off and the deflection is toward the left hand side. What are your basic observations here? Let's talk about it. When the primary circuit is closed, current grows from 0 to the maximum, right? When the key is on, current is growing from 0 to the maximum. During this period, changing current induces the changing magnetic flux. It means with the change, what changes here? With the change in the value of the current, the flux is also changing, right? During this period, the changing current induces changing magnetic flux across the primary coil. The changing magnetic flux is linked across the secondary coil and induces the EMF. Now, what is happening over here? Just pay attention to it. With a changing magnetic flux, which is linked across the secondary coil, the induced EMF and hence the induced current is formed across the secondary coil. So you'll have to keep focus to the primary first. When you'll be applying some current over here, when you'll be applying some polarity over here, potential over here into the primary, what is happening? Initially it was 0, then it starts growing, and then further what will happen? It reaches to the maximum value. It reaches to the maximum value, and once when it is reaching to the maximum value, because it is moving from 0 to the max, so what you will encounter, you simply can encounter here, dear students, that there is a change from 0 to the max. It means there is a change. So whenever there is a change, you find the development of the current. So that is why you just observed that galvanometer here was deflected towards the right when the key was on. It was deflected towards the right when the key was on. Just check it out again. Just check it out again. Deflection is towards the right. Just check. Furthermore, when the key is, so now I'm just taking out this key. The deflection is toward the, just check it out again. Deflection is towards the left hand side. So what is happening? You are growing from 0 to the maximum, and when you'll be taking out the key, you are going down from maximum to 0. So deflection you found in both the cases, right? Deflection you found in both the cases. And when this particular deflection you encounter is only when the flux is changing. When the flux is going from 0 to the maximum and from maximum to 0, then only the deflection can be seen. And when the flux is constant, there is no deflection. Furthermore, let me take you to the points again. So this is what we were discussing. The changing magnetic flux linked across the secondary coil and hence induced EMF current is found in the secondary coil. Furthermore, induced EMF and hence deflection in the galvanometer last only as long as the current in the primary coil and hence the magnetic flux in the secondary coil changes. So one thing needs to be very clear, that the deflection in the galvanometer can only be seen once when the flux is changing. It means 0 to max and max to 0. Under these cases only you find the deflection. Furthermore, if the flux becomes constant, flux is not changing, flux becomes constant, then there you do not find out any furthermore change, right? No deflection can be seen. Let us move on to the next, dear students. When the primary coil is open, current decreases from maximum value to the 0 value. During this period, changing current induces a changing magnetic flux across the primary coil. The changing magnetic flux is linked across the secondary coil and induces the current in the secondary coil. However, note that the direction of the current in the secondary coil is reversed, and hence the deflection in the galvanometer is opposite to the previous case. So this is what we just encountered. If you see, what they want to say is they simply want to talk about these things only. In this particular case, you find the deflection is toward the right hand side, and in the second case, the deflection is towards the left hand side. So this is what they are constantly talking about, right? So let us talk about the next thing, my dear students. These are a noteworthy point which I'll be sending it to you so that you can just have the note of it. Furthermore, let us talk about the next thing, that is Faraday's law of EMI. What is basically the Faraday's law of EMI? Let us discuss. So dear student, the first law, whenever there is a change in the magnetic flux linked with the circuit, an EMF and hence the current is induced in the circuit. So what we will have to keep in your mind, that the changing magnetic flux is a cause of the development of induced EMF or induced current. So what causes induced EMF or current is a changing magnetic flux. Till the time the magnetic flux will be changed, till the time it is changing, the EMF will be getting developed. Once when it will stop changing, what will happen? The EMF, induced EMF, will stop that time. So that is why it is written that, however, it lasts only so long as the magnetic flux is changing. Once when the magnetic flux stop getting changed, what will happen? It will remain stationary, it will not deflect. So one thing needs to be clear, that whenever there is a change in the magnetic flux, induced EMF will get developed. Furthermore, second law. So the magnitude of induced is directly proportional to the rate of change of magnetic flux linked with the circuit. So my dear students, one thing needs to be clear, that changing magnetic flux causes induced EMF or induced current. It means what is the cause of induced EMF or current? That is the changing magnetic flux. Once when the magnetic flux is changing, induced EMF and hence induced current is developing. How much induced EMF or current is developing depends upon the rate of change. It means one thing needs to be clear, that changing flux causes the induced EMF, and how much induced EMF will get developed depend upon the rate of change. If the extent of change will be more, induced EMF will be more, and if the extent of change is less, then the induced EMF will be less. Furthermore, what they'll be writing here is E is proportional to d phi by dt. Removing the proportionality symbol, you will have to add here k. E is equal to d phi by dt. Once when we take k is equal to 1. If you will be writing here k is equal to 1, then you can write here E is equal to d phi by dt, which further you can write here it to be as phi 2 minus phi 1 divided by t. Let us move on to the next thing, my dear students. The second very basic law, very important law, is Lenz's law. What Lenz law says, the direction of induced EMF or induced current is such that it opposes the change that is producing. Let me take you back to the points again. Dear students, if you see from these two diagrams, the direction of the supplied current in the primary is clockwise, and the direction in the secondary coil, just check it out, is anti-clockwise. So the supplied direction, just check in the second case also, the direction of the supplied was clockwise, right? Clockwise, and the direction developed is, means in this case, if you just check it out, in the primary case, when it is applied over there, just check it out, the first case, in this particular case, the direction supplied was clockwise and the direction which you will be getting is anti-clockwise. So dear students, what do they want to say? Let's talk about it. Okay. So what is happening? You'll be supplying the clockwise current, and what is getting developed? That is anti-clockwise current. So that is why it is said that direction of induced EMF or induced current is such that it opposes the change that is producing it. So what is happening over here? In this particular case, you'll have to remember one thing, that whatever is causing the induced EMF, induced EMF is opposing the same thing. It means the induced EMF always opposes the cause of its production. If the cause of production is a clockwise current, induced current will be anti-clockwise. It means induced current will be opposing the cause which is producing. That is, if the current is induced due to the motion of the magnet. For example, if the current is produced due to the motion of the magnet, then the induced current in the coil sets itself to stop the motion. If you simply see in the previous cases when we were talking about the coil, when the north of the magnet was brought closer to the coil, you simply see that the near face is developing the north polarity. It means coil was coming closer, means that magnet was coming closer with the north pole, right? The north pole was coming closer, right? And the polarity developed in the coil was north, so north and north were repelling each other. It means when the magnet was trying to come closer to the coil, what was happening? That coil was not allowing it to come closer, right? And when the magnet was going away, right, when the north pole of the magnet was going away, the polarity in the coil becomes south. It means it do not allow the magnet to go away. Means what? It simply shows that when the magnet was coming closer, coil was repelling it. When the magnet was going away, the coil is attracting it. It means neither it is allowing it to go away nor it is allowing it to come closer. So ultimately it is opposing whatever is happening with the magnet, right? So that is what, if the current is induced due to the motion of the magnet, then the induced current in the coil set itself to stop the motion of the magnet. Means ultimately what it do, what it want, it simply want the stoppage of the motion of the magnet. And once the motion of the magnet be stopped, change in the flux will be stopped, and change in the flux will be stopping the induced EMF. So it means what? Induced EMF always opposes the cause of its production. Let us talk about the next point. If the current is induced due to the change in the current in the primary coil, for example, now let us talk about it. If the current is induced due to the change in the current in the primary coil, then induced current is such that it tends to stop the change. This is what we are already discussing, with that the north and north polarity is developing, so coil is, that magnet is not coming closer. When the magnet is trying to go away, south pole is getting produced, so what will happen? Magnet will not be able to go away from it. Now let's talk about the next thing. Lenz's law and the law of conservation of energy. According to the Lenz law, the induced EMF opposes the change that produces it. It is the opposition against which we perform the mechanical work is causing the change in the magnetic flux. Now, what is happening here? If you simply see, induced EMF opposes the change that produces it. We already have studied it. It is that opposition against which we perform the mechanical work. Now, dear students, one thing is very clear, that whatever the work we are doing, whatever the work we are performing, whatever the energy expense we are doing, is producing one more energy. It means when the magnet was pulled or pushed towards the coil, you expense some energy to it. And because of the expense of that energy only, the induced EMF was getting produced. So what they want to say, they simply want to say that it is this opposition against which we perform the mechanical work in causing the change in the magnetic flux. So what is the magnetic flux? Why the magnetic flux is linking here is only because the expense of energy was done. Therefore, the mechanical energy is converted into electrical energy. So what is happening over here? The mechanical energy is converted into electrical energy. Thus, the Lenz law is in accordance with the law of conservation of energy. So we need to remember one thing, that Lenz law always obeys the law of conservation of energy. Lenz law always obeys the law of conservation of energy. It simply says what Lenz law says. Lenz law simply says that induced EMF always opposes the cause of its production. This is the statement of Lenz law. Now, why this? Because you are doing work against this opposition only. So you'll have to do some expense of energy. And once when you'll be doing some expense of energy, induced EMF is getting produced. It means the expense, what you will be doing in the form of mechanical work, that particular expense is leading you to the electrical energy. So this is what we need to understand. It means ultimately you are using some energy, and on an expense of that energy only, electrical energy will be getting produced. Let us talk about the next point. If, however, the reverse would happen, then a little change in the magnetic flux would produce an induced current, which would help the change of the flux further, thereby producing more current. The increased EMF would then causes further change of the flux, and it would further increase the current and so on. This would create energy out of nothing, which would violate the law of conservation of energy. Now let us try to understand what they want to say. They want to say here, if there is no such expense, for example, if you are not doing any mechanical work in pushing or pulling the magnet, what will happen? If the magnet is moving by itself closer to the coil and will go away from the coil, in that way, what will happen? This particular induced EMF will be an infinite source of energy. But we all know that there is no such infinite source of energy available in this world. It means if you are using some energy, then you'll be getting some energy. It means on an expense of your energy only, you will be getting another energy. So what is happening here, if this particular process will not take place, if you are not utilizing your mechanical work to get this electrical energy, then what will happen, you will be developing some infinite source of energy, and which is not possible. And till the time it is not possible, law of conservation of energy will be followed. And what law of conservation of energy says, dear students, law of conservation of energy simply says that energy can neither be created nor it can be destroyed. It can simply be converted from one form to another. So what is happening here, mechanical energy is converted into the electrical energy. Let us talk about the next thing. Expression for induced EMF based on both the laws. Let's talk about it. E is equal to minus d phi by dt. E is equal to minus phi 2 minus phi 1 divided by t. And for n number of turns of the coil, E is equal to minus n d phi by dt. E is equal to minus n phi 2 minus phi 1 upon t. It means we are simply writing here the value of d phi. What is d phi? The change in the flux, and change in the flux is equal to phi 2 minus phi 1. Expression for induced current, let's talk about it. You already know E is equal to IR. So I is equal to E upon R, and the value of E is already there with you. That is minus n d phi by dt, or d phi by dt, right? The value of E, that is what equal to minus d phi by dt, and divided by R is equal to I, because you already know E is equal to IR. So I is equal to E upon R, and the value of E is minus d phi by dt divided by R. Expression for charge, you already know I is equal to dq by dt, that is equal to minus d phi by r dt. Dt and dt will be cancelled both the sides. So dq is equal to minus d phi by r. If you simply see in these two cases, in the case here as well as the case here, in dq and in I, you will be getting the value, you will be getting some relation with r, but you are not getting any relation of resistance in the EMF. So let's clear one thing. Note, induced EMF does not depend on the resistance. It means this expression does not depend on the resistance. So what depends on resistance? Current as well as charges. Okay, method for producing induced EMF. Number one, you already know method for producing induced EMF. So induced EMF depends on what? Change in flux. And flux depends on BA cos theta. Right? We already know this. Phi is equal to BA cos theta. And induced EMF, E is equal to d phi by dt. So let's be very clear with it that induced EMF depends on the change of flux, and flux depends on the phi depends on BA cos theta. So first thing which will be responsible for the production of EMF is B. So magnetic flux phi can be changed by changing the magnetic field. We already know this. By changing the area, right? Now let's talk about the change in the area. How does this change the flux? So here you are having magnetic field, and which type of magnetic field you are having here is the uniform magnetic field, which is perpendicular to the plane of paper and cross represents directed inward. So here you are having this PQRS armature. It is moving towards the magnetic field. So previously it was having very less area in magnetic field. Now it is having more area in magnetic field. Now area is equal to length into breadth, right? Length, let's take the length, that is L. And what is breadth? Breadth is equal to velocity into time, right? Because breadth is what? It is the extent which is moving towards the magnetic field. So it is moving with velocity v, and in time delta t, it is reaching to this particular point. So breadth is equal to v into del t. So area is equal to length into breadth, right? So let's talk about it. Let's talk about it. So here I'm writing d phi. You already know phi is equal to BA. So d phi is equal to B dot dA, and dA, that is change in area, is equal to length into breadth. What is length? L. What is breadth? V dt, right? And you already know E is equal to minus d phi by dt. And once when you place here the value, you will get minus BLV. This is an expression for the motional EMF. This is an expression for the motional EMF. So once when the coil is going towards the field, it is equal to E is equal to minus BLV, and once when it is coming out of the field, it will be equal to plus BLV. So this is one should always remember, right? Let's talk about the next point, dear students. So here, according to the Lenz rule, the direction of induced current is such that it opposes the cause of changing magnetic flux. Here, the cause of changing magnetic flux is due to the motion of the loop and increase in the area of the coil in the uniform magnetic field. Therefore, this motion of the loop is to be opposed. So the current is setting itself such that Fleming's left-hand rule, the conductor PS experiences the force to the right, whereas the loop is trying to move in the left. Now, what is happening here? Let me try to explain it. What is going to get it happened? We can only understand this if we'll be knowing Fleming's left hand, Fleming's right hand rule. So what is Fleming's right hand rule? Fleming's right hand rule says that if the magnetic field is, if the forefinger is representing the magnetic field, thumb is representing the force, then the induced current will be represented by the central finger. So what is happening over here? If you simply see the previous diagram means what? If I can simply take you to the previous diagram, this is what I'm trying to tell you. Let's talk about it. Let us talk about it. If you simply see this particular diagram, in this particular diagram, what is happening? In this particular diagram, what you'll have to do is you'll have to understand if this particular armature is moving toward the left hand side. Toward the left hand side. So the motion is toward the right hand side. Right? And motion of the force will be towards the forefinger will be representing the direction of the field, which is inward, right? And the motion, right? Motion, force field current, or you can simply say the motion which is represented by the force which is in the upward direction, right? So what is happening? In because of this particular way, what is happening? The force or the motion will be towards the left hand side, so the direction of current will be downward. So what is happening over here? Let me try to explain you the concept, what they want to say here. Let me take you back to that point. Let me take you back to the point. Note, if the loop is completely inside the, okay, this one. Let me take you to this point. This is that point. Okay, this is the point. Therefore, this motion of the loop is to be opposed. So the current is setting itself such that Fleming's left hand rule, the conductor arm PS experiences the force on the right, whereas the loop is trying to move toward the left. So this is what I want to tell you. By using that particular Fleming's left hand rule, I want to tell you that the force which is there exerted by the induced EMF on the armature PQRS was toward the right hand side, and the PQRS armature is moving toward the left hand side. So by following Fleming's right hand rule, we get to know if the field is inward, force is represented by the thumb and induced current will be represented by the forefinger, then you get to know that the PQRS, which is moving toward the left, while moving toward the left, this induced current, induced EMF is trying to push that particular PQRS toward the right hand. It means it is even opposing the motion of PQRS. So this is what this particular Fleming's right hand rule suggests about the moving of the PQRS armature in the field. So dear students, let us talk about the next thing. The third very important factor means phi is equal to BA cos theta. You already have discussed about B, you already have discussed about A, and we'll be discussing about the orientation. So we need to understand these are the three factors which we'll have to keep in mind. So what we are doing is, first method for producing induced EMF. First one is B, second one is A, area, and third one is, after discussing all these things, after discussing all such points which I'll be making you to show again, I'll be moving toward the third thing. That is what? Changing the orientation. So what I'm going to do, let me take you to this point. This is the field. This is the armature PQRS, and it is moving with velocity omega. Now let me show you again. It is moving with velocity omega like this. Now let me take you to the point. This particular movement means the normal of the armature makes an angle of theta with a B. And you already know phi is equal to BA cos theta. And number of turns, if it is capital N, then it is NBA cos theta. At time t with angular velocity omega, it is moving. Then we can write here theta is equal to omega t. So what I'm doing is I'm replacing the value of theta, that is omega t. So NBA cos omega t. Differentiating both the sides, that is what d phi by dt is equal to minus NBA sine omega t. So E is equal to minus d phi by dt, right? E is equal to minus d phi by dt means phi is equal to NBA cos omega t. If we'll be differentiating both the sides, so it will be d phi by dt. NBA is constant. Cos omega t's differentiation will be sine omega t, and the differentiation of omega t will give you omega. So it comes out as what? Minus NBA omega sine omega t. And if we'll be sending this minus sign, if we'll be sending this minus sign towards the left hand side, so it will be minus d phi by dt, and the value of minus d phi by dt is equal to E. So E is equal to NBA omega sine omega t. Dear students, furthermore, NBA omega is the maximum value of EMF, so I'm writing here E naught. E naught is equal means E is equal to E naught sine omega t. That is a peak value. What is E naught? That is the peak value of the EMF. Furthermore, the EMF changes continuously in the magnitude and periodically in the direction. For example, if the EMF is changing continuously in the magnitude and its direction is reversing periodically with respect to time, then this particular EMF is known as alternating EMF. Just check it out. What I'm trying to tell you, it means if there is a constant change in EMF and there is a change in the and the periodic change in the direction of the current, then we can refer this particular EMF, then we can refer this EMF to be alternating EMF. And what is happening here? Just check it out. These are the angles. This is the time period in which these angles will be attaining, and this is the reference line, and this type of EMF we will get. So dear student, this is an alternating EMF. Furthermore, you can take this particular point to be E naught, that is the peak value of EMF, right? Furthermore, E can also be written E naught cos omega t. That is also possible. If the graph is cosine graph, you can plot the points, and furthermore, this type of graph can be attained. It means both these graphs actually represent the alternating EMF. So let's talk about it. So the alternating EMF and consequently alternating current can be expressed in sine or cosine functions. So dear students, this is what we need to remember, and this is the method for inducing EMF in the principle of generator. So this is a basic principle of the generator also. Furthermore, let's talk about the next thing: eddy current or Foucault current. This is the theoretical concept. My dear students, you must have seen the current in the wires, but what we'll be doing is we'll be seeing the current in the solid metallic pieces, right? What I'm going to do, you already know, when a huge current is passing through the wire, that wire will get heated up, and after excessive heating, these wire will get breaking, right? They will get broken up. So what I'm doing is, instead of making them to flow in the wires, I'll be making them to flow in the solid metals. Now this is the solid metallic block, this is the magnetic field, and this will be the direction of the Foucault's current, which will be, if the magnetic field is coming outward, then the direction of the current will be clockwise. Just check it out. So dear student, this current which you observe in the clockwise direction, this current is known to be as Foucault's current or the eddy current. Now why it is known to be as eddy current is because it will be in the form of eddies or the whirlpools, right? Eddies or the whirlpool, or you simply can say like the waves, right? And why it is known to be as Foucault's current is on the name of its inventor, its discoverer, right? Mr. Foucault. Application of eddy current: induction furnace. You must have seen induction furnace on which your father, your mother cook food, right? Eddy current can be used to see in the instantaneous speedometers too, deadbeat galvanometer, electric brakes, energy meters, and several others, right? So these are the areas where you can see the application of the eddy current. Furthermore, self-induction. What is the process? What is self-induction? It is the phenomenon of inducing EMF in the self coil due to the change in the current and hence change in the magnetic flux in the coil. So what I'm doing is, let's try to understand. One more point: induced EMF opposes the growth or the decay of the current. This is just the Lenz's law. Self-induction is also called inertia of electricity. Now this particular term you'll have to remember for your competitive examination. What is called inertia of electricity? That is the self-induction. And what is called the back EMF? Self-induced EMF. My dear students, if you'll be having the copy, you please write it down. Self-induced EMF is called the back EMF. Do not get confused. If somewhere it is written what is back EMF, then you'll have to remember self-induced EMF is called the back EMF. Let's talk about it. What is self-inductance? Phi is directly proportional to I. It means flux changing in the coil depends upon the current which is flowing across it. Or you can write here phi is equal to Li. What is L? L is the constant of proportionality, which is known as self-inductance or the coefficient of self-induction. If I is equal to 1, if the current flowing is 1, then L is equal to phi. It means coefficient of self-inductance, self-induction is numerically equal to flux if the current flowing in the coil is unity or 1. So this is how we can define it. Now furthermore, you can also write E is equal to minus d phi by dt, right? And you already know the value of phi. If you see here, this is a phi, d phi, and the value of phi is Li. So what I'm doing is I'm placing here the value of phi, that is Li. So E is equal to minus L di by dt. If di by dt is equal to 1, it means change in current is 1, then L is equal to E. Then L is equal to E. Let's talk about it. Thus, the self-inductance is defined as the induced EMF set up in the coil through which the rate of change of current is unity. If the rate of change of current is unity, dear students, if the rate of change of current is unity, right, then coefficient of self-induction or inductance is numerically equal to EMF. Let's talk about the next point. The SI unit of self-inductance is Henry, right? Self-inductance is said to be 1 Henry. Self-inductance is said to be 1 Henry. This is what they're talking about. Self-inductance is said to be as 1 Henry if 1 ampere of current is flowing across the coil. So this is what they are writing here. So furthermore, the second definition, the self-inductance is said to be 1 Henry when the rate of change of current is 1 ampere per second, induces EMF of 1 volt. So this is what they want to say. They are placing the value over here. If di by dt is equal to 1, then coefficient of self-induction, that is L is equal to E. So this is what they want to say. So these are the two different definitions which we already have discussed, and this is written in the wordings. You can just go through with them again. Self-inductance of a solenoid, let's talk about it. Let's have a coil of length L, area A, current flowing is clockwise. Now you already know the expression of magnetic field of the solenoid, that is mu naught Ni. What is small n? Small n is turns per unit length. What is small n? What is small n if I write here? Small n is equal to what? Turns per unit length, that is capital N upon L. So you further may write magnetic flux linked across one turn of the coil is, for one turn, what you will do, phi is equal to Ba. So the value of B is what? Mu naught Ni, you will place here, multiplied by A. Right. Furthermore, if you will be replacing a small n by capital N, you will have to write here mu naught Nia by small n. What is the small n representing? It is the length of the conductor. Furthermore, magnetic flux linked with n turns of the coil, because here it is having n turns. So magnetic flux made by n turns is this much. Magnetic flux linked with n turns is equal to this much. It means what? We'll be multiplying this factor by capital N. So what further you'll be getting? Phi is equal to Li. You already know. You'll be replacing here the value from these two expressions. What you'll do? You'll place here the value, right? So phi is equal to Li. I and I will cancel. So L is equal to mu naught N square A by L. Or you can write here mu naught N square A into L. So these are the expressions which we will be getting. This is energy in an inductor, which has nothing to do with the chapter, but you will have to remember this we studied in the previous chapter. That is what? Let me take you to it. That is what? The expression of the energy. That is what? Half Li square. Furthermore, let's move on to the next. Mutual induction, my dear student. Mutual induction says what? It is a phenomenon of inducing EMF in the secondary coil due to the change in the current in the primary coil. So what is happening here? EMF is inducing in the secondary coil due to the flux which is changing in the primary coil. So do remember, mutual induction means what? Thing is happening in the secondary because of the change which is taking place in the primary. So this is what we need to remember. Furthermore, mutual inductance, you can write here, changes happening in the primary, that is in the 1, and experienced by 2, that is secondary. So I'm writing here phi 2 1 is directly proportional to I1. It means current is flowing in the primary, that is what I1. So phi 2 1 is proportional to I1, right? Phi 2 1 is equal to M I1, where M is the constant of proportionality and is known as mutual inductance or coefficient of mutual induction. If I1 is equal to 1, for example, if you'll be placing here the value of I1 is equal to 1, then M is equal to phi, right? The mutual inductance is defined as the magnetic flux linked with the coil in the secondary coil when the unit current flows through it. So this is what they are writing, right? Whatever is the expression is given over here, simply they have written it into the English language. Furthermore, E is equal to minus d phi to 1 upon dt. What is phi to 1 represent? That changes taking place in one experienced by a second. Right, that is what the mutual inductance is happening over here. So E2 is equal to minus d phi to 1 upon dt. Furthermore, you will be placing at the value of phi to 1, that is mi1. So you will place here, right? So if you will be writing here di1 by dt is equal to 1, then m is equal to E. So what is happening? Rate of change of current is in the primary coil is 1 and it induces the EMF. So mutual inductance is numerically equal to induced EMF when the rate of change of current in the primary coil is 1. So this is what they are writing here. Let me tell you again. Thus, the mutual inductance is defined as the induced EMF setup in the secondary coil when the rate of change of the current in the primary coil is unity. The same. Its SI unit is also Henry. Mutual inductance is said to be 1 Henry. Mutual inductance is said to be 1 Henry. This definition is from here, right? This M is equal to 5. So what I'm doing is mutual inductance is said to be 1 Henry when 1 ampere of current, when 1 ampere of current, when 1 ampere of current is in the primary coil linked with a magnetic flux of 1 Weber across the secondary. Or the second definition comes from here, this one. Mutual inductance is said to be 1 Henry. Mutual inductance is said to be 1 Henry when unit rate of change of current 1 ampere per second from here, 1 ampere per second in the primary coil induces EMF of 1 volt in the secondary coil. EMF of 1 volt in the secondary coil. Let's talk about the next one. Mutual inductance of two long coaxial solenoid. This is primary. This is secondary. Current flowing. This is the galvanometer is attached to the secondary. Length of the primary and the secondary is L. Area is A. Current flowing in the primary is I1. Right? So now what is happening? Magnetic field due to the primary solenoid is B1 is equal to mu naught N1 I1. Now here I am writing magnetic flux linked across one turn of the secondary solenoid is phi 21 is equal to B1A. What is the value of B1? That is mu naught N1 I1 into A. That will give you mu naught that will give you mu naught. Now small n1. Small n1 I am writing here capital N1 divided by L. Right? So I'm writing here mu naught N1 I1 A by L. So this is the flux which is produced. Right? Magnetic flux linked across one turn. Now you'll have to talk about n turns. When you'll be talking about n turns means secondary coil cut turns, what you'll do? Phi 21 is equal to here from you are already getting mu naught N1 I1A, mu naught N1 I1A divided by L, and it is multiplied by N2. Why I am multiplying it with N2 is because this flux which is produced by the primary coil will be associated with each and every turn of the secondary coil. So that is why I am multiplying it with N2. Let's talk about the next point, my dear student. Phi 21, that is the mutual inductance flux, that is equal to the M21. Now what is M21? That is what mutual inductance associated with the secondary coil due to the first coil. Now here I am writing M21 is equal to mu naught N1 N2 A by L, which you can write here it to be as, means what I have done here, I have placed here the value, means from these two expressions. This is also the expression, this is also the value of phi 21 and this is also the value of phi 21. So what I did, I have placed them together. So from this I1 and I1, they'll be cancel out each other. So here you'll be getting what M21 is equal to mu naught N1 N2 A upon L. Furthermore, my dear students, you can place here in term of turns per unit length, right? So if you'll be writing here in form of turns per unit length, it will be mu naught small n1, small n2, A into L. Do remember small n is what? Turns per unit length. What is capital N? Total turns. Furthermore, M12 is equal to this particular term. If you see both of them, both of these values are similar. So they follows reciprocity theorem. For two long coaxial solenoid of same length and cross-sectional area, the mutual inductance is same and lead to the principle of reciprocity. Furthermore, my dear students, what it says, mutual inductance means M is equal to M21, which is equal to M12. Now, what does it mean? Mutual inductance made by first experience by second will always be equal to mutual inductance made by second experience by first. Means both of them will have the same numerical value. Furthermore, additional information, if two solenoids are wound on a magnetic core of relative permeability mu r, then what you will do? You already have studied this expression. Now you multiply this expression by mu r. You will be multiplying this expression by mu r. Just check it out. Furthermore, my dear students, if R1 is less than R2, right? If R1 is less than R2, then what you will do? You will always multiply the area. This area will be equal to pi a smaller radius square. It means what you will have to do is you will have to keep in your mind that the radius will be of the smaller terms, right? Furthermore, mutual inductance depends only on the relative placement of the solenoid. Furthermore, means this point you will have to understand mutual inductance only depends on the relative position of the solenoid. It means if both the coils are totally wound over one another, mutual inductance will be more. But if there will be a little less, mutual inductance will decrease. So the extent of their relative position, their relative placements over each other or from each other will give you the magnitude of the mutual inductance. Coefficient of coupling K between the two coils of self inductance L1 and L2, what it will be? K is equal to coefficient of coupling is given by K, that is equal to coefficient of mutual inductance divided by under root L1 L2. Here K should always be less than 1. Furthermore, for the series, L is equal to L1 plus L2. For parallel, 1 upon L is equal to 1 upon L1 plus 1 upon L2. And this ends the class of the day.